So we're going to start today by talking about the scientific method. The scientific method is a process that scientists use to generate and evaluate new ideas, as well as to evaluate previous ideas from other scientists. Scientific method is going to be important as it outlines a general plan that scientists apply towards solving problems. Alright, so let's take a look at the various parts. There are going to be several parts that we need to keep in mind when considering the scientific method. First part is going to be observations. We make observations about a problem, and we take those observations and we form a hypothesis. Now that hypothesis may require us to go get something called peer review, where we go and get outside feedback from people and see if they agree with our hypothesis about our observations. We can also do further experimentation to test our hypothesis, which involves more observations. So you can see kind of a circular approach here where we do observations, form a hypothesis, do additional experimentation, which involves more observations, and so on. Now with that additional experimentation, we can also have outside peer review done. Alright, but let's first focus on the first part there, observations. Observations can be both qualitative and quantitative. So let's look at these a little bit closer here. Alright, let's start with qualitative. Qualitative observations could be things like color. They mainly involve observations that do not involve a numerical measurement. However, that doesn't mean you can't use numbers in qualitative observations. They're just not numbers involved with the measurement. For example, you could use a label to indicate the beaker on the right in the picture to be beaker 1. That's a qualitative observation that's using a number. Now the other type of observation is quantitative observations. Quantitative observations are going to use numerical measurements. An example of this would be that there are 3 items in the picture. 2 of the items have blue solutions. The green solution has a volume of 15 milliliters. All of those numerical values used involve measurements of some sort. Alright, let's run through some examples. For each example, identify whether the example is going to be quantitative or qualitative. I'll pause for a few seconds to give you the opportunity to make that observation. So, number 1, a piece of metal is longer than the piece of wood. Is that quantitative or qualitative? Well, that would be a qualitative observation because there's no numerical measurements involved. Even though you're saying one is longer than the other, you're not actually doing measurements, so it would be qualitative. Alright, number 2. Solution 1 is much darker than solution 2. Is that quantitative or qualitative? That would be a qualitative observation. Even though numbers are involved, they're used a way to identify each solution, but not any actual numerical measurement. We could also call them solution A and solution B to distinguish between them. That would be qualitative as well. Alright, number 3. The mass of the solid was 4.56 grams. That would be a numerical measurement, therefore it would be a quantitative observation. Number 4. The liquid in beaker A is blue. Well, those would be qualitative observations since there's no numerical measurements involved. Number 5. The temperature of the liquid is 60 degrees Celsius. That would be a quantitative observation as there is a numerical measurement involved. So this gives you a basic idea of quantitative versus qualitative. Alright, let's talk a little bit more about observations and some problems with them. Alright, you need to be careful when making observations that you don't confuse fact with opinion. So let's look at an example of this. Watching television is a waste of time. Many people feel that this statement is a fact. However, Many people feel that this is not true and that the enjoyment received from watching TV is important. So really, watching television is a waste of time is really just an opinion. Now, a way around this being just an opinion, if you look at a scientific study and you collect data to study people who watch television versus waste of time, if you could somehow set up an experimental design involving that, you could change this statement from an opinion to a fact. But you need scientific data to back any statements up. If you don't have scientific data to back anything up, it's just an opinion. And you need to be careful about making opinions with your observations instead of just factual observations. You also need to be careful of something called inferences. All right, what's an inference? Well, let's look at an example. You see that a policeman has pulled over a man driving a red sports car. All right, why was the man pulled over? Some people may come up with various reasons, one of which they may say the man in the red sports car was speeding. However, you have no facts about this. You have no idea whether that's actually true or not. All you know is that the car has been pulled over. In fact, you don't even really know that. All you know is the car has pulled over and is off to the side. Could have been several different reasons for why it was off to the side of the highway. So, you need to be careful about inferring things into your observations. You need to just state facts and not draw conclusions before you get all the facts. So once we've made enough observations, we can begin to form a hypothesis. So what's a hypothesis? Some people say it's an educated guess. Let's get a little bit better definition than that. It's a little bit more to it than just that. Hypothesis is really a proposed explanation of observable experiences. Okay, so let's take a look at forming a hypothesis. It's around dinner time and you see spaghetti boiling in a pot on the stove. So what do you think you're having for dinner? Well, we could hypothesize that we're having spaghetti and meatballs for dinner. That's one hypothesis we can draw from that observation. From that hypothesis, then, we need to do further experimentation to test that hypothesis, which involves making more observations. So let's go back to our example, and let's say we have a hypothesis that we're having spaghetti and meatballs for dinner. So how could we test this hypothesis? How could we do further experimentation with this hypothesis? We could check to see what other ingredients are currently being used in the kitchen. Does there appear to be tomato sauce? Does there appear to be Parmesan cheese if you have that on your spaghetti? You can also check to see if there are meatballs made. If we see no sign of meatballs or spaghetti sauce, then you could adjust your hypothesis to reflect these observations. You could say you're just going to have plain spaghetti with no sauce. But it all involves further experimentation, and sometimes we do have to adjust our hypothesis. So this system gets to be very circular, and it's very important. Make observations, we form a hypothesis, we do further experimentation on that hypothesis by making more observations. Now it's going to be important though at times that we get outside review. Okay, in other words, that peer review. So peer review is going to involve an outside source. We need someone who's going to be impartial to your findings. Typically, that peer is going to review the results of someone's findings to agree or disagree with their conclusions or their hypothesis. They may also conduct experiments on their own to try and reproduce results of other experiments for confirmation of the hypothesis, or they may come up with new experiments to test the hypothesis as well. So let's look at an example of this. You smell something with a bad odor. You ask a friend to smell it as well to confirm the odor is bad. That's a simple view of it, but it is peer review. You've run an experiment, you smell, it smells bad. You get someone else to confirm that the odor is bad as well. Let's look at a little bit more practical view of this. You run an experiment in a lab and obtain results. You ask another person in the lab to double check those results. What does it mean to double check those results? Well, they may check their calculations, they may run the experiment again. But once again, you're getting this outside source to evaluate your information. Now, when we look at the real scientific world, a more practical application of this is when we have reviewers for articles on experiments that are to be published in scientific journals. So when people come up with experimental findings, they write up a paper, submit it to a journal. That journal then sends those papers out to professionals in those specific fields to read that paper and review it to see whether it's worthwhile to go into the journal or not. Peer review, though, is a very, very important part of the process because we always want confirmation from others to get that outside perspective to see if we've made mistakes or drawn bad conclusions. Also, it's to just get confirmation and get everybody to agree to the same findings. All right, so we've gone through that circular process of making observations, forming a hypothesis, doing further experimentation, getting peer review. Now we're going to talk about something called a law. A law is just going to be a summary of behavior. We can use that law then to predict future behavior. We can then do further experimentation to support or prove laws, right or wrong. So let's look at an example of this, what do we mean by that summary of behavior. Let's look at the law of conservation of mass, which states, in a chemical reaction, matter is neither created nor destroyed. So, what does this mean? Well, if we look at burning methane gas, take methane, CH4, we react it with oxygen, O2, and we get CO2, carbon dioxide, and water, H2O. When looking at this, if we start with 16 grams of methane and we react it with 64 grams of oxygen, we get 44 grams of carbon dioxide and 36 grams of water. Total on the left-hand side, what we started with was a mass of 80 grams. On the right-hand side, we get a mass of 80 grams. So based upon this law, we started with 80 grams, we end up with 80 grams, even though we get different compounds. So matter is neither created nor destroyed. This law is just stating behavior of chemical reactions. So by running these chemical reactions, people started to see this trend where what mass they started with was the mass they ended up with. That's how we came about this law of conservation of mass. So law is a summary of behavior. A theory, on the other hand, is going to be an explanation of behavior. So a theory, it's going to be hard to conclusively prove whether it's true or not, but by doing further experimentation, we can support it or find error with it. A theory often isn't just a simple statement, but consists of multiple parts. Okay, so let's look at an example of this. Atomic theory. Now there's lots of parts to atomic theory. One part of that is that atoms of an element cannot change into atoms of another element in a chemical reaction. Atoms simply change the way in which they are bound to each other. So let's go back to our example of burning methane. We had CH4 reacting with O2 to form CO2 and water. If we look at the structure of CH4, you can see a carbon with 4 hydrogens around it. We have 2 oxygen double bond molecules. CO2 is just a carbon double bonded to 2 oxygens. And then we have 2 water molecules. Each one consists of an oxygen bonded to 2 hydrogens. So we can see number of carbons on the left and the number of carbons on the right are the same. Number of hydrogens on the left and the number of hydrogens on the right are the same. Number of oxygens on the left and the number of oxygens on the right are the same. All we've done is rearranged how they're connected. That's part of what the atomic theory states. All right, so let's look at this law versus theory again, just to kind of summarize them. All right, remember, a law is going to be a summary of observations. We start with 80 grams, we end with 80 grams. Law of conservation of mass. We get that by doing multiple experiments, seeing this same observation over and over again, and we create the summary of that observation. Theory then is going to be an explanation of behavior, basically stating that the atoms are rearranged in such a way to form new compounds. They're similar in that they both typically come from numerous testing and peer review until a consensus about them is reached. But if you look at these again, law, summarizing observations. Theory is explaining why we're seeing those observations. Okay, and that's the distinction we want to make between that. And that pretty much wraps it up for our discussion of the scientific method.